Complete and balance the double replacement neutralization reactions, then write the net ionic equation. So to create net ionic equations, there's a series of steps. Step 1 is to start with the balanced molecular equation. This is the equation that just shows all of the reactants and products in their combined forms, their molecular or their ionic forms. Step 2 is to dissociate strong electrolytes. So what you're going to do is you're going to break apart any ionic compounds that are strong electrolytes. In other words, any ionic compounds that are soluble in water or aqueous in our balanced equation. If we are doing an acid-base neutralization reaction, any strong acids or strong bases that are present need to be broken apart, dissociated, and shown in their ionic form with their charges. Step 3 is to identify spectator ions. Spectator ions are ions that are present when the reaction is taking place, but they're not participating in the reaction. Just like a spectator at a sporting event doesn't participate in the actual event, they're just present and watching. Step 4 is to eliminate those spectator ions. We remove them from the equation. So anything that is the same on both sides of the equation, that means the same charge and the same phase on both sides of the equation, we can simply remove it. And then step 5 is to write the net ionic equation. We just write whatever's left over, and at this point it should actually already be balanced. So to write net ionic equations, we have to know which compounds are strong electrolytes and which are weak electrolytes or non-electrolytes. And to do this, you have to know your solubility rules for ionic compounds. In general, group 1 and group 2 cations, any compound that contains a cation from group 1 or group 2, is going to be soluble. So sodium compounds like NaCl, or potassium compounds like K2SO4, or something with a group 2 ion like calcium, CaNO32. These types of things are going to be soluble. They're going to be strong electrolytes. Anything that is a nitrate compound, an acetate compound, or an ammonium compound is also going to be soluble. In general, compounds that contain halides like chloride, bromide, and iodide are going to be soluble, but there are a few very important exceptions. Silver compounds and lead-2 compounds, as well as mercury-1 compounds, are insoluble. So, for example, silver chloride is a very common insoluble ionic compound. Sulfates are generally soluble with a few important exceptions, and those are calcium sulfate, strontium sulfate, barium sulfate, and lead-2 sulfate, as well as mercury-1 sulfate. So you notice that the halides and the sulfates have a few things in common. A lot of lead compounds are generally insoluble. A lot of mercury compounds are generally insoluble. So this is something that you have to know and memorize, but it is an important concept, so make sure you spend some time remembering these things. Okay, so our first reaction is sodium hydroxide and magnesium chloride. The first step is to write our complete molecular equation. We want to make sure that we always include phases here because those are going to become important later. So we'll write our reactants first. Sodium hydroxide in the aqueous phase plus magnesium chloride also in the aqueous phase. And this is a double replacement reaction, so we are going to swap cations. Cations here are Na plus and Mg2 plus. The anions are hydroxide, OH minus, and Cl minus. So we're going to switch places, and we end up with NaCl. Now we have to stop here and ask, what phase is sodium chloride going to be in here? Well, this is a very soluble compound. It's a group 1 metal and a halide. So because this reaction is taking place in water, we know that this is going to be aqueous. It's a strong electrolyte. The other compound that's formed is magnesium hydroxide. Always make sure that you're following your rules for crisscross when you're creating ionic compounds so that you end up with the right formulas. Now, magnesium hydroxide is a hydroxide, and hydroxides are often insoluble. And if you have to consult a solubility chart, if that's available to you, to figure out whether this is soluble or insoluble, you need to do so. But it turns out that this is a very insoluble compound. And so this is going to be in solid form. This is a precipitation reaction, a double replacement precipitation reaction where we will get solid magnesium hydroxide as a product. We now need to balance this equation, and that's going to be relatively simple to do. We just need to put a 2 right here and a 2 right here, and so all of our atoms are balanced on both sides. The next step is to separate all of these strong electrolytes into their separate ions. So what we're going to do is we're going to look at anything in this case that's in the aqueous phase. Those are the strong electrolytes. Those break apart in water, so we're going to show that. So NaOH is going to break apart into 2 sodium ions because there are 2 moles of sodium hydroxide, so we're going to get 2 moles of sodium ions. Those are in the aqueous phase. We do want to make sure that we keep putting our phases here. We're being very careful about that because that's going to be important when we start canceling spectator ions. There are also 2 hydroxide ions that are also in the aqueous phase. Our magnesium chloride is also split apart into ions. Mg2+, we have 1 of those. And because the subscript on the chloride is 2, we are going to get, oops, I forgot my phase. I'm going to go ahead and put that in there. This magnesium is aqueous. Those ions are dissolved in water. And I have 2 chloride ions that are also aqueous. On the other side of my reaction, I'm going to have to put this on a separate line. On the other side of my reaction, I have 2 sodium ions that are in the aqueous phase. I have 2 chloride ions that are in the aqueous phase. But my other product, which is magnesium hydroxide, is a solid. It is a non-electrolyte. It does not dissolve in water. And so we are going to write that as magnesium hydroxide. We're just going to keep it together in the solid phase. Now what I have to do at this point is I have to identify my spectator ions. I want to look at the ions that are the same on both sides of my equation. Now they have to match in coefficient, they have to match in charge, and they have to match in phase. And so on my reactant side, I have 2 aqueous sodium ions, and on my product side, I have 2 aqueous sodium ions. So those are spectator ions. Those can be eliminated from each side. And so this is going to disappear. This is going to disappear as well. I have 2 hydroxide ions in the aqueous form on the reactant side. But on the product side, my hydroxide ions are in a solid compound. They are not in the same phase. They're combined with magnesium, so I can't cancel those. On my reactant side, I also have a magnesium ion in the aqueous form, but over here it is bonded to hydroxide in a solid, so it will not cancel. My other reactant is 2 chloride ions in the aqueous phase, and here on my product side I also have 2 chlorides in the aqueous phase. And so I am going to cancel those out as well because those are spectator ions. And then all that's left to do is now to write my net ionic equation, the equation without spectator ions. So I'm going to take what's left over, and the things that are left over are my magnesium, my hydroxide, and then my magnesium hydroxide solid on the product side. So it should already be balanced if you're doing everything correctly. I'm going to take magnesium, and I'm putting the positive ion first just to be neat, because that's the way I know it's going to combine. And then I'm going to combine that with 2 aqueous hydroxide ions. To form magnesium hydroxide solid. And that is my net ionic equation. The next 2 reactions deal with acid-base neutralization reactions. And so we have to know which acids are strong electrolytes. Now, an acid that's a strong electrolyte is an acid that dissociates completely when it dissolves in water. These are also known as strong acids. I want you guys to memorize the 6 strong acids that are very, very common. These are HCl, HBr, HI, HNO3, H2SO4, and HClO4. In addition, you have to know your strong bases. In general, any base that is any hydroxide that comes from group 1 or group 2 metals like sodium hydroxide, calcium hydroxide, these are going to be strong bases. They are strong electrolytes. They dissociate completely in water. Now, if it's not part of this list of strong acids, or if it's a hydroxide of a transition metal, for example, it's going to be a weak acid or a weak base. And those are weak electrolytes. They do not dissociate 100% in water, and so they only partially ionize, which means that in our net ionic equation, they are going to be shown in their combined form, not separate. They are not going to be spectator ions. Okay, so here we have an acid-base neutralization reaction. We have sodium hydroxide, which is the group 1 hydroxide. It is a strong electrolyte, strong base. And we have HCl, which is shown in its aqueous form because it is a strong electrolyte. It's a strong acid. So, first thing we have to do is write our complete molecular equation. So we have sodium hydroxide in its aqueous form plus HCl in the aqueous form, and that is going to yield, because this is an acid-base neutralization reaction, the 2 products that we're going to get are water, which is in the liquid form, and our salt, which comes from the cation from the base and the anion from the acid, which in this case is just NaCl. Now, NaCl is a strong electrolyte, and so because this reaction is happening in water, this will be aqueous. So now what we have to do is separate all of our ions. The equation is already balanced. So we have Na plus aqueous, OH minus aqueous, H plus aqueous, Cl minus aqueous. Those are our reactants. And then on the product side, we have H2O, which is a liquid, so we have to keep it together. This is not an electrolyte. It's a molecular compound, so it stays together. Na plus aqueous and Cl minus aqueous. So now we're going to identify the spectator ions, the things that are the same on both sides, and eliminate them. Both sides have an Na plus ion in its aqueous form. We can cancel that. Both sides have a Cl minus ion in its aqueous form. And so to write the net ionic equation, we are going to use what's left over, which is simply H plus OH minus makes H2O. If you have a strong acid and a strong base, this will always be the net ionic equation. For the last example, we have a strong base, sodium hydroxide, reacting with HF. Now, HF is in the aqueous form because it is dissolved in water. However, HF is a weak acid, which means it does not dissociate 100%. And so this reaction is going to be slightly different than the last one. It's got different rules. So we're going to start off, as usual, by writing our complete equation. So we have NaOH in the aqueous form, reacting with HF. We're going to switch, or we're going to get water and a salt the same way that we would get in any other acid-base neutralization reaction. And the salt that we get in this case is NaF, which is a strong electrolyte, which means that it will be soluble in water. It will be in the aqueous form. So now what we're going to do is the same thing we did before. We're going to separate our strong electrolytes into their ions. Sodium hydroxide is a strong base, so it is going to become Na plus in the aqueous form, plus OH minus in the aqueous form. However, HF we are not going to separate. We are going to leave that together because it is a weak acid. It is a weak electrolyte. Most of it remains undissociated. And so we simply leave it as HF in the aqueous form. On the other side, we have H2O, a molecular compound, stays together as a liquid. And we have our strong electrolyte, sodium fluoride, which we're going to separate into its ions, Na plus and F minus. So now we're going to eliminate any spectator ions. Well, there's only one. Sodium is going to disappear, but everything else is different on either side, and so it's going to stay together. And what we end up with is HF, aqueous, our weak acid, plus OH minus, our hydroxide ion. And essentially, what happens in this reaction is that hydroxide bumps into HF and essentially rips off the H to make H2O liquid and a fluoride ion. So this looks a little bit different than our strong acid, strong base net ionic equation because our weak acid, HF, is still part of the net ionic equation.